video, we're going to be talking about solution dilution. So we use the version in chemistry M1V1 equals M2V2, where M is the molarity and V is the volume. If you plan on working in a science lab or biology, chemistry, if you want to be a pharmacist, this is an equation that you'll need to use almost every single day. I promise you. This equation, or very similar versions of it, actually has applications outside of science as well. Anybody who works with solutions needs to know how to prepare a dilution. When I was in college, my roommate was studying to become a manicurist. She wanted to do nails. And she had to use this equation to prepare the disinfecting solutions in order to sterilize all the tools in between the different clients. So I can't emphasize it enough. This is an important topic for chemistry, but also for many different career paths and honestly for life. In this first problem, we're asked to prepare 1 liter of a 0.646 molar hydrochloric acid solution. However, what we have on hand is a 2 molar hydrochloric acid solution. How do we do this? So the first thing is to identify the matched sets. What I mean by that, 1 liter belongs with 0.646 molar. That's what we're shooting for. That's what we want to prepare. So those two values should have the same subscript. It doesn't matter if you use the 1s or the 2s, but because they belong together, they need the same subscript. I'm gonna arbitrarily label them V1 and M1. So either I label them on my paper, or if I don't have a printout, I'll write it over here in the margin. But always label all your variables ahead of time. It helps a lot. 2 molar, I'm gonna call that M2. So that means we're solving for V2. How much of that more concentrated 2 molar hydrochloric acid solution do we need to grab in order to prepare this solution? Now we plug and chug into the M1V1 equals M2V2 formula. So I'm going to start with 0.646 molar, and we're going to multiply that by 1 liter. M2 is the 2 molar. And we're solving for V2. So to get V2 by itself, I'm going to have to divide both sides by 2.00 molar. The units of molarity cancel, leaving me with units of liters. And then these two things cancel completely, and we're just left with V2 on the right-hand side there. So I will plug this into my calculator exactly like this with a big set of parentheses around the numerator, and then I'm going to divide by 2 molar, and I get a value of 0.323 liters. What does that mean? Because again, remember, this is a practical scenario. This isn't something we just do on paper. This is something chemists do every single day in the lab. So V2 goes back to M2. Those two things belong together. So this means I need 0.323 liters of the 2 molar solution. However, if I'm in the lab, it's more likely that I'm going to work in milliliters. So I'm going to convert this over to milliliters. So we need 323 milliliters of 2.00 molar HCl. Okay. That's fine and dandy, but the problem asks us to describe how to prepare the whole solution. And we need 1 liter or 1,000 mils total. So what does all this mean? First, we're going to put 323 milliliters of 2 molar hydrochloric acid. The rest of the volume to get us up to 1,000 milliliters is going to be DI water. So we need to figure out, we're going to do 1,000 milliliters minus 323 milliliters. And that's going to tell us how much DI water we should put. So here we need 677 milliliters of DI water. When we combine these two things, the 323 milliliters of 2 molar hydrochloric acid with the 677 milliliters of DI water, we'll get exactly 1 liter of 0.646 molar hydrochloric acid solution. How would you prepare 60 mL of 0.2 molar nitric acid from a 4 molar stock solution? What are they talking about, a stock solution? Well, that's going to be something that you have on the shelf already made in your lab. Typically, stock solutions are more concentrated than what you anticipate needing in your experiments. The reason being is because it's pretty easy to dilute things down by adding some water. But the opposite is difficult to do. It's hard to concentrate things, if not like impossible in some cases. So labs will typically have a bunch of concentrated solutions ready to go on the shelves, and we call those stock solutions. In this problem, we assume that the stock solution is the nitric acid, that they have the same component in them, even though it wasn't explicitly stated. Since it's a dilution problem, we're going to use that formula again. M1V1 equals M2V2. We're going to carefully go through our problem and label all the numbers they gave us. So we'll do V1 here, and it belongs with the 0.2 molar, so that'll be our M1. We have an M2 here, and V2 is unknown. So we're trying to figure out how much of that 4 molar solution we need to prepare the 0.2 molar solution. Plug and chug into the equation. So 0.200 molar times 60 mils. And let me stop real quick right here. You can use milliliters in the M1V1 M2V2. You can use any units you want for volume as long as they match on both sides. Or in this case, since we're solving for V2, if we use milliliters for V1, our units for V2 will also be milliliters. You only have to convert to liters if you're using the molarity equation. Molarity equals moles over liters. However, here, don't convert. It's just an extra step and it could lead to a mistake. So keep it as milliliters. Equals 4.00 molar times that unknown volume. Let's divide each side by 4 molar to get the V2 by itself. And when I plug this into my calculator, I'm going to put a big set of parentheses around the numerator. I'm going to do 0.2 times 60, close parentheses, divided by 4. Units are canceling. Molarity cancels with molarity, leaving us with milliliters. And the answer here should have 3 sig figs. We're going to have 3.00 milliliters equals V2. What does that mean in terms of preparation? So we're going to need to grab 4 molar nitric acid. Specifically, we're going to need 3 mils of that 4 molar nitric acid. Then the rest of our solution, since we're going for 60 mils total, will be water. So 60 minus 3 gives us 57 mils of DI water. So practically speaking, we're going to do 3 milliliters of 4.00 molar nitric acid and 57 mils of DI water. And by mixing those two things, we're going to wind up with 0.2 molar nitric acid solution. This problem is a little bit different from our previous two problems. In the previous two problems, we were asked to figure out how to prepare the solution. This one already tells us what they did, but the approach is going to be the same. We want to start by labeling the numbers that they gave us. So we have 12.5 milliliters of 12 molar hydrochloric acid. So we'll call this V1 and this M1. And then they added a bunch of DI water, and that's an important clue. That's how we recognize it as a problem that uses M1V1 equals M2V2. It's definitely a dilution problem if they're adding DI water. And then the final volume is 200 milliliters. This time, we're asked to solve for the resultant concentration. What is M2? What is the concentration after they added that DI water? Plug and chug. So we have 12.0 molar times 12.5 mils equals M2 times 200 milliliters. We want to isolate M2, so I'm going to divide each side by 200 milliliters. The units are canceling nicely here. So milliliters cancel milliliters, and I'm left with a concentration unit, molarity. Plug it into my calculator, and I get M2 equals 0.750 molar. Makes sense. It started out as 12 molar, but they only had a little bit. They only had 12.5 mils. They added a bunch of water, got it up to 200 milliliters total volume, but now the concentration, since they added all that water, the concentration dropped quite a bit. So final answer is 0.750 molar. This problem is very similar to number 3. So we're asked to solve for a final concentration after somebody already did the dilution. We're given V1, and we're going to recognize that as V1 because of the units, milliliters. M1, and then V2, and we're solving for M2. The fact that they're talking about diluting the solution helps us realize that we need to use the M1V1 equals M2V2 formula. Plugging everything in, we have 3.50 molar times 75 milliliters equals M2, which we don't know yet, times 400 milliliters, the final volume. In order to get M2 by itself, we're going to divide each side by the 400 milliliters. Checking that the units are canceling. Milliliters cancel milliliters, we're left with molarity. And when I plug this in my calculator, I figured out that M2, that final concentration after diluting, equals 0.650 0.05625 molar. Making sure to use the units. We also have to check sig figs. Looks like we're down to 3 sig figs because of the M1 and the V1 values. So I'll report my final answer here as 0.656 molar. Number 5 is a very open-ended problem, and there's multiple correct solutions. It's kind of vague. I like it though. So one student might approach this in a very straightforward manner, in a similar way to numbers 1 and 2. They recognize that we have a V1 and an M1 right here. We're given the target concentration, and we'll call that M2, which means we need to solve for V2, the total volume of the diluted solution. So we can plug and chug 0.125 molar times 505 milliliters equals 0.100 molar times V2. We're going to divide both sides by 0.100 molar. Units will cancel. And that's going to give us an answer of 631.25 milliliters. That's great. And some of you probably got that value, but it's critical. I need you all to be able to interpret that value. So first off, always check, what does this volume correspond to? So here we have M2.100 molar. That's our diluted solution. So at the end of the day, we would have 631.25 mils of 0.100 molar hydrochloric acid solution. This also indicates our total volume. So if our total volume is 631.25 mils, we can go ahead and subtract the amount of hydrochloric acid that we started with, and that's going to tell us how much DI water was added. So we're looking at 126.25 mils of DI water. This problem is interesting because some of the questions, I didn't write them down, but some of the questions that are in this problem ask us about glassware. So if we were taking this approach, we would have to use graduated cylinders. So you would verify that you're dealing with exactly 505 milliliters of the starting solution, and then you would use your graduated cylinder to obtain exactly 126.25 milliliters of DI water. You would mix them both together, and then at the end, after you mix, you would have 631.25 mils of 0.100 molar hydrochloric acid. However, graduated cylinders are great for measuring volume in a lot of applications. In your at-home lab kit, that's all you have. So you should definitely be using the graduated cylinder to measure volumes. However, in the lab, we have access to higher precision glassware. And so I want to do this problem again, especially because of the word exactly, and show you another possible answer that makes use of this precision glassware. This is a volumetric flask. It's a piece of precision glassware that we use in the lab when we're looking to prepare solutions that are exactly a certain concentration or a certain volume. The thing about the volumetric flask, it's great because it's super precise, but you only have one option with the volumetric flasks. For instance, this is a 250 milliliter volumetric flask, and so my total volume would have to be 250 milliliters in order for me to use this. I would fill it with the DI water up to this little white line in the neck. Kind of expensive too. That's another downfall. However, we get precision out on the other end. I want to approach this problem again with the mindset that I need a really, really exact solution, so I'll be using a volumetric flask. This is a random number, and the number we got when we solved this problem earlier is also kind of random. The volumetric flasks come in pretty specific increments, like whole number increments. You can get a 10 milliliter, a 50 milliliter, a 1 liter, but you're not going to be able to get a 505 milliliter volumetric flask. So when we set this up, we can still use 0.125 molar as M1. And our target concentration, our M2, won't change either. We're still shooting to prepare a 0.100 molar solution. However, what's going to change is the volume of this final solution. So thinking that I want to use a volumetric flask, and they didn't say how much we need, but just to play it safe, let me pick a value that's a little bit less than what we have here. So let me make 500 milliliters of my 0.100 molar solution. That means I need to figure out how much of the 0.125 molar solution I need. I can use up to 505 mils. So if we're approaching the problem this way, with the idea that we're going to decide upon the volume of the final solution, this piece of information almost becomes extra. It just tells us how much we have available, but we don't necessarily need to use the whole amount. So once again, we're going to do M1V1 equals M2V2. And I'm going to plug and chug. So we have 0.125 molar, and then V1 is unknown, M2, and then the total volume that we decided upon so that we could use the volumetric flask that we have. Solving for V1, I get 400 mils. So V1 corresponds to 0.125 molar. So I'm going to take 400 milliliters of 0.125 molar hydrochloric acid solution. I'm going to put it in my volumetric flask. It'll be twice the size of this one, but there are 500 milliliter volumetric flasks available. That's a pretty common increment. And then once I put the 0.125 molar hydrochloric acid in here, then, I mean, you could do the subtraction. You're like, well, then I'm going to need to add 100 mils of water. But you just take your little DI water squeeze bottle and you fill it up to this line with DI water. You don't even try to calculate it and measure it separately. You know that the total volume is 500, so you just fill the rest with DI water.